All right, well, just to put a cap on the thing I was just saying, I mean, certainly like to answer Jackson's question with a little more fullness, if you have like a rotation of 45 degrees in the plane or something like that, that's a function that takes every point and specifies exactly, like, where does the point 3, 4 go? Well, it goes to the point, I don't know, there's something different, right? Someone, and it outputs a point. You give me a point, say it's a rotation around the origin, you give me the origin. Where does the origin go? The origin under a rotation around, right? But every other point specifies, for every point, specifies where it will go. That's a function from R2 to R2.
So any function is just something where you input something and get an output?
Right, yeah, as long as there's a uniquely defined output, right? Like, as long as it's not like you say, well, where does the point 3, 4 go? And then you give me like 2 answers. Like, it goes to this point and also this point. Well, okay, that's a little problematic. Right?
Okay, but isn't that what you're doing when you have like a parametric function? You're like, well, like, where is the point?
Well, it's just you're outputting. You need to think of a point as one thing, is all, right? Instead of like, it's not 2 outputs, it's 1 output, but it's a order pair. It's an object. You're taking in objects and outputting objects. You're not taking in a single number and outputting a single number. That's not what a function is defined to be. Single input, single output. But by input and output, we mean those things very generally, not just like a number, right? Yeah, and even something as simple as addition is a function from R2 to R, isn't it? Right? You take 2 numbers, you give me 2 inputs, I return 1 output. Yeah. So this is just not a discussion we have a lot in high school in terms of, even though it's, you know, so this kind of operation is called a binary operation. You've probably heard that, right? If you're computer scientist, you probably know about binary and unary operations and stuff. Anyway, so the point is, like, it's okay to talk about these functions is the point, and then call them functions too. So certainly t squared, if you graph this on your calculator, you remember how to do this. Let's just refresh your memory on the calculator. You go to set a function, go to parametric mode, type in, instead of y1, y2, etc., you'll have x1t, y1t, and it won't even blacken these equal signs and let you graph it until you've entered 2 things, right? And when you press your xt, comma, x, comma, t, comma, beta, comma, n button on your calculator, it just automatically gives you a t. And t is often used as the parameter when we're talking about parametric functions, sometimes s, other places near that in the alphabet. But t makes sense because a lot of times what we're talking about is motion. We're talking about some motion, and where are you in the plane at a given time? So that's maybe a good reason to use t. I think that's actually the default window, maybe. Anyway, so if you do this on your calculator, you'll get a picture something like this. And notice that when you trace your graph, you'll get 3 things you're tracing, and also in the window, you also have control over a new set of values, to t-min, t-max, t-step. All stuff you hopefully are familiar with from pre-calculus. But let's just review as we're tracing here. If we're at t equals 1, of course, we output 1, comma 1. So that's not a surprise. If you were to eliminate the parameter, and do you remember how to do that? Someone walked through the parameter. It's not interesting to me, maybe, but this is x equals t, and this is y equals t. Well, if x is t, I guess it makes sense that y equals x squared is really what we're looking at, which is what we saw in the picture too. So that's not a huge surprise there. So keep in mind that eliminating the parameter, you might be thinking, like, wouldn't that always be desirable? But there's a sense in which this communicates the same trajectory for a particle, but this doesn't tell us, it tells us where the particle was, but not when it was at each place. And that maybe matters. Here's a second parameterization for the same curve. Right? If you eliminate the parameter here and divide by 2 and plug it in here, you'll see that you get also y equals x squared. It's the same curve. And if you graph it, you get the same picture. T squared, 2t, 4t squared. Same curve. But notice now, what's different? Well, we're at the point 1, 1 when t is 0.5, right? So there's a sense in which you're like moving more slowly along this curve or something, right? So I want to make sure you're kind of thinking about parametric equations in this form. And of course, we can ask about the derivative. In fact, this is review 2. And we did this when we introduced the chain rule last semester. We just kind of said, really briefly, we said, by the way, this can be used to calculate the derivative of a parametric function. So we'll do that in a second. But even asking about the derivative, before we say that, we need to specify that there are 3 things someone could even be asking about here, because there's so many variables to think about. someone might care about, and I want to make sure we're interpreting each of these correctly. dy dx is kind of a typical one. Notice that that really has nothing to do with, in terms of like someone caring about the time. That's really just asking the age-old question on the path, the trajectory we're looking at. What is the actual slope, y with respect to x? We're talking about like the slope of the trajectory, the actual motion. What does dy dt mean, though? What does that mean? Yeah, and if we're thinking about motion, that's like the velocity in the y direction at a given time, right? And dx dt would be like the velocity in the x direction, or the change in x per change in t. So that's kind of measures the horizontal change and vertical change, right? Your calculator, if you go to the calculate menu, when you're in parametric mode, your options are different than normal. And you'll see available to you when you're on your calculate menu in parametric mode, these values, including the 3 derivatives we just mentioned. So then, like I said, from first semester, dy dx is just this stack, right? Change in y over change in t, over change in x over change in t. In some sense, you can think, well, the dt's cancel out. And that's an okay way to think about it. It's not like 100% mathematically rigorous because we're dealing with infinitesimals. But that is just a recapitulation of the chain rule. Do you remember? I mean, do I have that? I don't have it up here, but remember that the chain rule, the reason we introduced this earlier in this year was that the chain rule, one way of writing the chain rule is to say dy dx times dx dt equals dy dt. Right? This is the, at least in Leibniz notation, one way of saying the chain rule. I don't know if you're into that. So we said if we divide both sides, even last semester we said we can get this and do a parametric function. So we had, I think on homework we had a couple problems like that, but I'm sure that's not, it wasn't really a focus then. So returning to our example here, if we want dy dx, and I've got this extra subscript 1 because remember we had 2 examples, right? We had t squared and also 2t, 4t squared. So in the first set, we get 2t as the derivative dy dx. Keep in mind that gives like the slope at a point that's not the, we almost never, if we're thinking about motion and velocity and all that, dy dx never gives like a velocity, right? It still gives like the slope on the curve. dy dt, dx dt, those are velocities, components of the velocity in both directions. That's an important thing to say. For the second equation, we get a different derivative, dy dx, for the slopes, and that's 4t here. Notice, where am I getting the 2t and 1 and the 8t and 2? 8t comes from just differentiating this with respect to t over here. So in some sense, this might feel like, oh, this might feel like the quotient rule broken or something. Like this shouldn't be using the quotient rule. But we said, actually, the math supports us just doing this, right? Take the derivative with respect to t, take the derivative with respect to t, and divide, right? So I'm thinking that maybe that sounds a little bit familiar. I hope. And of course, these should agree, though, you would think. Well, they do agree, but keep in mind that this one, the t values on this one, are different for the different points than for this one. So notice that if you are on the first curve and t is 1, that tells you that the slope right here, and this is believable, at the point highlighted, is 1. Does that look like 1? Yeah, of course. Yeah. Well, down here, what would you have to plug into 4t to get the same answer? Well, of course, you're plugging in 0.5, and that gives the same answer too. So you might at first have thought, like, this shouldn't these agree? They're the same curve. But of course, for each curve, we have the different parameterization, so that matters.
Aren't they both equal to 2?
They're both equal to 2. They're both equal to 2, is what I meant. Yeah. Do you remember what this picture looks like? That's the definition of what? Yeah, circle, or in particular, the unit circle. Right? So I'll show you that picture in a second. So we have, in some sense, again, we have the horizontal motion described in one equation, the vertical motion described in the other. Together we have uniform circular motion. now the screen makes it look like an ellipse, but you understand. Hit zoom squared, you'd see it as a hoop. And if you were, I don't know that this will be a focus of what we're doing here, but certainly it's true that if you eliminate the parameter here, and just think about what would happen if you took this squared plus this squared, you would get 1, wouldn't you? But, I mean, that's the Pythagorean identity, right? And by cosine t we mean x. So what is x squared plus y squared? Well, it's cosine squared plus sine squared. Well, what's cosine squared plus sine squared? 1. Right? So that's the equation that you would normally have for that. It might just not be obvious. It's very clear how to eliminate the parameter in the last example. But here you might be thinking, how did we do that again? Well, consider what x squared plus y squared is. Plug in cosine and sine, you'll see that you get 1. So let's work with this quickly. Can we express this as a function of t, dy dx? Yeah, the derivative of cosine is negative sine, so that goes on the bottom, negative sine. And the derivative of sine is cosine, so that goes on top. So we get negative cosine over sine. And that's a fine way to write it. I'm actually going to keep it this way for now, even though I think some of you might be tempted to write a negative cotangent or something. This would be fine. But I think it's helpful to see it this way just because we're about to ask these questions. So where does this have horizontal tangents? When will that happen? That is, when is dy dx 0? So when does that happen? Look at the fraction. When t is what? You know, when we're asking when does cosine equal 0, right? When does the numerator equal 0? I have them come up here. Yeah, pi over 2, 3 pi over 2, all right? And of course that agrees with the picture too, right? Pi over 2 is where we get a horizontal tangent. So it's not maybe a huge shocker, but I want to show you in this example. What about sine t? When is that 0? Well, now, won't that make this dy dx undefined? Isn't that what we're looking for root of the tangent? So when is sine of 0? When is sine t 0? The answer is, of course, when t is 0, or pi, or 2 pi, or any multiple of pi. And there you see them. I mean, even if we didn't have the equation, if you just looked at this, someone would say like, oh yeah, at 0 radians, pi radians, you're getting the vertical tangent. But the calculus supports the intuitive approach too. The second derivative, again, recall from first semester, it's a little messy, is the same thing we had before. Just take one more derivative of dy should I say this right? The equation that you had from before, here we'll do it with this one here. The equation that we did a second ago is dy dx equals cosine t over negative sine t. So that's dy dx we said. So if we take the derivative of that again with respect to t, d dt of that, in the numerator, that's negative cotangent, so the derivative of that is cosecant squared. And in the denominator, we just have dx dt, and so we already said that's negative sine that comes along, and we have an answer there for the second derivative. Let's see if we can see, is this okay to, I want to make sure that we're okay with why this is written this way too. So dy dx, what does this actually mean? Let's say what that means. Maybe by d to y, we literally mean d dx of dy dx. That's always what we mean by the second derivative of with respect to x of y, the derivative of the derivative. And dy dx So, and then by the chain rule, I mean, obviously I have a dt here, so how does that come out? Well, the chain rule allows us to take the derivative of something with respect to a different variable, if you like, as long as afterwards you multiply by dt dx. So that is what this says, right? If you divide by dx dt on the bottom, right? So this is just one more use of the chain rule. The second derivative, this right here, means this. And by the chain rule, we can swap out x for t as long as we multiply by the derivative of t with respect to x afterward. And that is what this says if you flip this and put it underneath. Sorry, I'll stop there for a second. Don't you have a question?
Oh, no, I figured it out when you were doing that explanation. I was going to ask why you divided by the derivative of x.
Yeah. So, I mean, you can just, I think it's good to just maybe try to have a little understanding of why that works the way it does. And the answer is just go back to the chain rule. It's a little bit complicated to think about maybe. So again, in some ways that's review though too, right? It's been a while. Other questions or thoughts so far? We're going to close today with just, like I said, a lot of this has been reviewed, but we're trying to put this all packaged nicely together. So let's actually go through this example here. And this is on the back. We've got lots of interesting questions, including one new question that is definitely not reviewed. So I don't know that I would expect you to do this without a calculator, but you could start plotting some points if you like and get a decent picture. But feel free to get your calculator out and graph this, or use Desmos or something, whatever your favorite technology tool is. Just make sure that really you know how to press the buttons here. Can you put it your calculator parametric mode? Do you know how to enter those two equations in to get this picture? Do you know how to make your t min and max be -1 and 1.5 on the window? Let's see if we can get a decent picture. So I'll give you a second to do it, and then I'll show you my picture.
So it says sketch the curve. You just plot it like that.
Yeah, for this one, right? Now, like you said, you could, with a little bit of labor, like, get a decent picture of this by just plugging in points. Plug in -1, plug in -1.5, plug in 0, right? And just step your way through it and try and get a feel for it. But I'm not sure that anyone, like, looking at that is like, oh, what, are you kidding me? You don't know what that looks like? Like, I don't think anyone blames you for not immediately knowing what that looks like or something. So see if you can generate a picture of this. Yeah, you may need to zoom in a little bit. It's small. Like I said, I'll put my picture up here. See, if you zoom in pretty close, you'll get this little thing. Like I said, you need to zoom in a little bit, or adjust your window as mid or as max, and blend in one there. Those that are done with this or not entertained by it, let's find dy dx. And here, of course, when we find dy dx, it'll be in terms of t. So give me an expression for dy dx in terms of t, based on the stuff we've just been talking about on the previous slide. Those corrections due on Monday. I don't know what this gets in this case decided, but I don't think that doing it to me tomorrow is fair. So give you a little bit of extra time to do it materials to me on Monday, so I can get into the grade book. All right, so hopefully you got this picture. I'm gonna ask for some participation on some of these questions too here. I think this is not too bad. There, C, how about, you want to give me a derivative here? 3t squared. Maybe he said that, I don't know. No, I wrote that down without thinking. Okay, yeah, that looks good to me. That's all that's asking for. I might need to copy that over here again. Here, let's write that on this slide too. dy dx equals 1 minus 3t squared over 1 minus 2t. Okay, good. Give the equation of the tangent line to the curve when t equals negative 1/3. So go ahead and take a second to do that. What do you need to do that? You need, now we're just talking in like normal rectangular coordinates, right? With y's and x's, give me an equation for the tangent line to the curve. So what three things do you need? You need an x coordinate, a y coordinate at the point of tangency, and the slope. But having t and having these three things, I think you could find those three things you need. So go ahead and do that. It'll be a little messy. Feel free to use your calculator in like fraction mode or whatever you want to do. And I'll that one is or I'll get you on this next one maybe if you can think it. I don't know what to do. We haven't really talked about that too much, but maybe you can figure it out. You got it? Yeah. Someone confirm all those. Let me just spot check some of this here. 2/5, that comes out nicely. Let's see here. I'm going to try this at t equals negative 1/3 here. I'm going to check your slope. Yeah, 2/5 is the slope. So I'll just assume that you did equally careful work on the x and y coordinates. Okay. I don't know. Someone else will call you out if they're wrong. But you see how you can do this? I'm just throwing a whole bunch of questions that could be asked in parametric form. Find the equation of the tangent line, find the derivative, find the, I think I have the second derivative down further here right on the page. All sorts of things we can ask. Do you have any insight onto this one, Laura? On D? How would you? Yeah, help us out. This is an interestingly worded question. Yeah, so say more. Like, why does that make sense? When is x has max? That was really good. When does x have a max? Sorry, my head is like congested. your x belong to us. Okay. When does x have a maximum? Is the question, right? For what value of t is x at its maximum? So what does y have to do with this? And the answer is nothing, right? So yeah, she's right. I mean, and I liked how you even said, let's apply the first derivative test to the x to t, right? That's, huh? Sorry. Peak form here today. Okay. Apologize. Yeah, so did someone want to take us away on that? I mean, this is not too bad. What's dx dt? And what do we do there? We're looking for where it has the derivative is either 0 or undefined. Of course, this is a nice polynomial thing, so it's just, we're looking for when it's 0. So that happens when t is like 1/2, right? Now, we're not completely done. We also need to say something about like how the first derivative test justify that that is a maximum. There are kind of two ways you can do that. You can either use the first derivative test and do a little number line like we've done before. And you'll see that if you plug in values to the derivative that are less than like 0, you'll get something positive. If you plug something bigger than 1/2 in, like 1,000,000, you'll get something negative. So the derivative goes from positive to negative. That means that the function, dx dt here, that means x goes from increasing, the x value of the x coordinate, right, goes from increasing to decreasing. That is, up until 1/2 on the timeline, the x value is getting bigger, and then after that, the x value is getting smaller. We're thinking horizontally here, right? So we didn't actually identify the rightmost point, though, did we? What do we still need to do? Yeah, let's actually plug in now 1/2 into our equations, and I don't know, does someone have that for us? 1/4? I agree with that. Comma 1/2 minus 8 is. By the way, is that believable from your picture? You could trace on your calculator and hit, when you're tracing in parametric mode, you'll be typing in 0.5, right? So trace there and you'll see it blinking. Should be right here, right? That rightmost point, just to confirm that we're like making sense here. Find the horizontal and vertical tangents. Let's see if you learned something from before. Laura, you want to take this one? Just get us started. Yeah, go ahead. Is that on yours, right? Yeah, find horizontal and vertical tangents. How do you do that? Good, she's right. Okay, so let's actually do that. So this one we get t equals that 1 over root 3, right? And here we get, actually plus or minus that, right? And here we get t equals 1/2. This is not a huge surprise here. By the rightmost point we just did, we also mean the place where there is a vertical tangent, right? So this is not a surprise that we get an overlapping answer here. Now, we didn't actually find the horizontal and vertical tangents. What is the equation of the horizontal tangents at these two places? By the way, does it look like there are two horizontal tangents in the picture? Where are they? One's down here. Where's the other one? Yeah, right there. Right, as you round the top, there's a little horizontal tangent there too. So this should give those two, I think, in this picture, hopefully. These are both in the intervals, so hopefully that'll work. Well, these have the form y equals, this one we already have. This one has the form x equals, and what is it? At x equals 1/4, right? This one, though, we need to plug in these two values to get these two horizontal tangent equations of these two horizontal tangents. So the first one is y equals well, I don't know, these are terrible, right? Plug in to the y equation this number. I don't know. Right, let's just write 1 over root 3 minus 1 over root 3 cubed or something. We can approximate that or something that's messy. And also negative 1 over root 3 plus 1 over root 3 cubed. Let me see if there's another interesting question on here. The second derivative, let's skip. For now, it's an interesting question though, actually. But the one thing I wanted to make sure I equipped you with is this formula. And this formula is on your sheet, so you have it. But if you want to find the length of this curve on your calculator, you can just run this. And these are usually integrals that are hard to do. So we usually, often, just like we did with arc length before, we'll be using fn to do these. So integrate for this curve from -1 to 1.5. And you've already computed these a million times. This is, was it 1 minus 2t squared plus 1 minus 3t squared. All of that dt, sorry. So yeah, I mean, if you were to try to simplify this integral and do it by hand, I think you'd have some trouble with that. So just fn int that and you'll get an answer. And I should say too that if you go back to our arc length PowerPoint, you remember like when we first thought about arc length of a curve, we actually started with this, and then we messed with this so that we could get it into the form. The arc length formula we like it, we remember is this. Remember that? But that was us. Yeah, sorry. Thank you guys. You guys keep me honest. That, remember, we got after doing a lot of algebraic manipulation with this expression. I don't know if you remember the arc length lesson when we were doing it, but the very first thing we said is divide up your curve into a whole bunch of little line segments. And then on each little segment, do change in y, change in x, like calculate the length of that segment. How do you get the length of that segment? Well, of course, it's just the Pythagorean theorem, right? Because it's the diagonal of some change in y, change in x. Right? So that's actually how we started that back then, if you go back and look at our notes. And then from that, we derived this. So it's actually not a huge surprise that we're seeing that again. It's just, at that time, we were like, well, we can't do anything with this expression. And the answer is like, actually, if we're working in parametric coordinates, it's actually really easy to work with. Oh, there we go. 5.136, if you want to write that down, is what you got. Notice that if you're working in parametric coordinates on your calculator, you can just use, sorry, my writing on top of this is obscuring a little bit, but notice that you can just use, from your variables menu, these two values if you want. You know, if you plug these into the derivatives into x and y. Let's not do that.